Alrighty, so here we have our first problem. The position of a particle moving on the x-axis is modeled by the equation that, where t is measured in seconds and s of t is measured in inches. For this problem, we're going to need the position function, which we have. It's given to us. And that inequality is just to show us that we're using time. We're using positive time, so time is greater than or equal to 0. The other thing we'll need is the velocity function, which is the derivative of the position function. S prime of t is the same thing as v of t. And that is equal to 36 minus 24t plus 3t squared, which is the answer to A. So here, I'll put A here. And the velocity after 2 seconds, you can just plug in 2. So v of 2 is equal to 36 minus 24 times 2 plus 3 times 2 squared, which is actually equal to 0 inches per second. 0 inches per second. So, what is really interesting about this value is that is when the particle is at rest. So it's not moving forward, not moving backward, which is also the answer to C. However, we know 2 is a 0, but we don't know that 2 is the only 0. So we have to set in order to find the other 0, we have to set the velocity function equal to 0, which is 36 minus 24t plus 3t squared equal to 0. And after doing some math, let's see, we got 3 factor out to 3, 8t plus t squared is equal to 0. Let's see, we got that 3t minus 6, t minus 2 is equal to 0. Alright, so here we got t equals 6, so that's a 6. Here we got t equals 2, that's equal to 0. So our times are 2 seconds and 6 seconds. And that is when the particle is at rest. When is the particle moving forward or to the right? Well, the particle is moving forward or to the right when the velocity function is greater than 0. So what I did to solve this problem is you just have to set up a table. So we know 2 and 6, star these because we know these are our zeros. This is when the velocity is equal to 0. So, make a little table here. We have to test values between 2 and 6, between 2 and 0 because we can't go lower than 0, and between 6 and infinity. So, let's test 3, 0, because it can be equal to 0. 0 is always an easy one to test. And 10. So 2 and 6, we know it's both 0. The answer is 0. Here. 3, after plugging it in to the velocity function, you get out negative 9. 10, you get out negative 96. And 0, you get out 36. So this is positive, negative, positive. So between 0 and 2 and 6 and infinity, the velocity will turn out positive, which means that the particle is then moving forward or to the right in our case. Alrighty, so I went ahead and set up E to save some time. But what E was asking was to find the total distance traveled in the first 10 seconds. Now, at s of 0, after 0 seconds, the particle is where it started. 0 seconds, 0 inches. Alright. After 2 seconds, it's traveled 32 inches. And I got that 32 inches by plugging the 2 into the original position function, that. And after 6 seconds, it's traveled back to where it started at 0 inches. So in the first 2 seconds, traveled 32 seconds. And then the next 4 seconds, 32 inches. In the next 4 seconds, it's traveled 32 inches back to where it started at. And then, in the next 4 seconds, between S of 6 and S of 10, it's traveled 160 inches, so it's sped up quite a bit. To find the total distance traveled in the first 10 seconds, we have to add all of this up, which is equal to, let's see, that is 224 inches. Another way people solve this problem is they do absolute value and just do, let's say, absolute value of S of 0 minus S of 2 plus the absolute value of S of 2 minus S of 6, and so on, and you'll get the same answer. Alright, so once again I set up F for us to save some time, and what F asked us to do was to draw a one-dimensional position diagram showing the path of the particle as it moves on the x-axis. So, here we have here we have our x-axis, and here we have 0 inches from where it started, and 32 inches. So at time t equals 0, it started at 0 inches, and then it traveled to the right, and at t equals 2, it was at 32 inches. But then, it traveled backwards, and in 4 seconds, at t equals 6, it got back to its starting position. And then, after t equals 6, it kept going infinitely onwards. Alright, now moving on to G. That's an easy one. Find the acceleration of the particle at time t and after 2 seconds. So, the acceleration, a of t, that's the same thing as the derivative of the velocity function, which is the same thing as the second derivative of the position function, which is equal to negative 24 plus 6t. And if we plug in 2, that's equal to negative 24 plus 6 times 2, which is equal to negative 12 inches per second squared. Alrighty, so letter I is asking us when is the particle speeding up and when is it slowing down. Now, the particle is speeding up when its acceleration and velocity have the same sign, and is slowing down when the velocity and acceleration have opposite signs. So picture this is you, Jimmy's running through a field, and you're running this way, and all of a sudden a gust of wind blows this way. So you're in the positive direction, gust of wind blows the negative direction. That's going to slow you down if you're running into a really strong wind. However, if you're running in the positive direction, and the wind, cross out that wind, and this wind blows, all of a sudden gusts and blows on your back, powering you forward, that's going to speed you up. And it works the same if these were both negative directions, if you were running backwards per se. So that's how speeding up and slowing down works. Now, to find when it's speeding up and slowing down, we're going to have to find the sign changes of the velocity and acceleration function. So, we had already made a velocity table, and I just kind of quickly sketched it out again, because it was on another piece of paper. When time t equals 2 and 6, the velocity is equal to 0. So between 2 and 6, the velocity is negative. That means between 2 and 6, the particle is moving backwards. And between 0 and 2, the particle is moving forwards. Between 6 and 6 plus 6 and whatever is after 6, it's moving forward as well. So we have the values and the sign changes for our velocity function, but we need to find it for our acceleration function. So we have to find when a of t is equal to 0. So our acceleration function is negative 24 plus 6t, so you have to set that equal to 0. 6t is equal to 24, and that comes out as t is equal to 4. And then after plugging in a value less than 4, a of 3, that's negative 6. Oh, we have a sign. And a of 5 is positive 6. Oh look, a sign. So concluding from that, we have 4, t equals to 4. And everything after 4 is going to be positive, and everything before 4 is going to be negative. So we need to find when the particle is speeding up and slowing down. So speeding up, as I said before, the acceleration and velocity signs are going to be the same. So at between 2 and 4, because everything less than 4 is negative, and everything from 2 to 4 is also negative. That's going to be when it's speeding up. But the signs also equal each other after 6 seconds, because after 6 seconds for the velocity times, it's always going to be positive. And after 4 seconds, it's always going to be positive for the acceleration times. Now, it's slowing down in between 0 and 2 seconds and 4 and 6 seconds. And here's why. In the velocity function, if t is any number in between 0 and 2, it's going to come out positive. However, in the acceleration function, when t is less than 4, it's always going to come out negative. And those are negative and positive, different signs. So, when t is in between 0 and 2 seconds, it's slowing down. Also, in between 4 and 6 seconds, if we look at the velocity function, it's going to be negative. However, anything after 4 in the acceleration function is going to be positive. Again, different signs. So, when t is in between 4 and 6 seconds, the particle is going to be slowing down.